Hello students, welcome to EPG Pathshala. I am Dr. Ajit Kumar Mahapatra from the Department of Physics and Astrophysics, University of Delhi, India. Today we are going to discuss about the module called Backscattering Spectroscopy, and there we will study about the Rutherford scattering part 2 from the paper Characterization of Materials 2. So students, let us see what we are going to learn in this module. First, we learned about the concepts of kinetic vectors, scattering cross section, energy straggling would be discussed, and in second, we will learn about the quantitative analysis on backscattering process. In third, we will discuss about the concept of Rutherford backscattering, and this is a introduction. There are four physical concepts govern the backscattering spectrometry. These are kinetic vector, scattering cross section, stopping cross section, and energy straggling. Kinetic vector gives information on the elastic energy transfer between the projectile and the target. The likelihood of occurrence of scattering leads to the concept of scattering cross section. The concept of stopping cross section gives an idea of the energy loss when the incident particle moves through a dense medium. Finally, statistical fluctuation in the energy loss of the scattered particle can be estimated through the concept of energy straggling. We would focus on the above mentioned concept in this session. Scattering cross section. So far, we have established the relation between the energy E0 of the incident particle of mass m1 and the energy that this particle possesses after an elastic collision with another particle of mass m2 scattered at an angle theta. Note that m2 is in a stationary state before and after the collision. In order to estimate the frequency of such a collision that really occurs at an angle theta quantitatively, concept of differential scattering cross section denoted as d sigma by d omega is important and will be described in details below. A narrow beam of incident particles falls on a target which is thin and uniform. If we place a detector at an angle theta from the direction of incidence, then it can count each particle scattered in the differential solid angle d omega as in figure 1. The differential scattering cross section d sigma divided by d omega is defined as d sigma d omega is equal to 1 divided by nt multiplied by dq by d omega whole divided by q, where q is the total number of particles that have hit the target and dq is the number of particles recorded by the detector. N is the volume density of atoms in the target and T is its thickness. Thus, Nt is the number of target atoms per unit area, which is also called areal density. It follows that the solid angle d omega is so small that the scattering angle theta is well defined. Note that the thickness T is assumed to be minimal and therefore the energy loss of the particles in the target is so small that the energy of the particle is virtually the same at any depth in the target. It is worth noting that Q must be large enough to have the ratio dq by q as a well determined value. The dimension of the differential scattering cross section d sigma by d omega is that of an area whose meaning is based on the geometrical interpretation of the probability that the scattering will yield a signal at the detector. We suppose that each nucleus of an atom exposes an area d sigma by d omega to the beam of incident particles. We also assume that this area is small and they are randomly distributed inside the target and they do not overlap with each other. Let S be the surface area of the target hit uniformly by the beam, then the total number of atoms for a scattering event in the target is S, N and T. The ratio of the total cross-sectional area of each such atoms S, N, T d sigma by d omega to the area S actually participated can be defined as the probability that the scattering event will be recorded by the detector. This ratio is equal to 1 divided by d omega dq by q dot d omega inverse. In the above expression is due to the fact that increasing the solid angle d omega twofold would double the number of counts dq. By dividing dq with d omega, this geometrical contribution to the number of counts dq is eliminated. The unit of cross section is a value per unit of solid angle. Hence, the term differential scattering cross section arises. The number of scattering events falling within a finite solid angle omega can be described by the integral scattering cross section defined as sigma is equal to integration over d sigma by d omega multiplied by d omega. Its geometrical interpretation is analogous to that of the differential scattering cross section. The solid angle omega falls in the range of 10 to the power minus 2 or less in backscattering spectrometry, and the scattering angle theta is well defined. The average differential scattering cross section sigma is equal to 1 divided by omega integration of d omega by d sigma multiplied by d sigma. The average differential scattering cross section is called scattering cross section and is used in the literature. The total number of detected particles A then can be written as A is equal to sigma multiplied by omega multiplied by q times n t, which is equal to sigma times omega multiplied by the total number of incident particles multiplied by number of target atoms per unit area. The above equation shows that any parameter can be estimated provided the other factors are known to satisfy this equation. The ability of backscattering spectrometry to provide quantitative information on the number of atoms present per unit area of a sample stems from equation 4, and the fact that the average scattering cross section sigma of the elements is known quite accurately. Differential scattering cross section for elastic collision is given by d sigma by d omega times c is equal to Z1 Z2 e square all divided by 4 EC sin square theta c divided by 2 whole square, where the subscript c indicates the center of mass frame of reference system that is considered here. Here Z1 is the atomic number of the incident particle with mass m1 and Z2 is the atomic number of the target atom with mass 2. E is the electronic charge, which is equal to 4.8 into 10 to the minus 10 starts coulomb, and E is the energy of the incident particle just before scattering. This formula is valid also for values in the laboratory frame of reference, but only when M1 is much less compared to M2. For the general case, the transformation of this formula from the center of mass to the laboratory frame of reference is given by d sigma by d omega is equal to Z1 Z2 E square divided by 4E whole square times 4 divided by sin 4 theta multiplied by 1 minus m1 divided by m2 sin theta square to the power half plus cos theta whole square divided by 1 minus m1 divided by m2 sin theta whole square and to the power half, where the first omitted term is of the order of m1 divided by m2 to the power 4. The last expression shows the functional dependence of the Rutherford differential scattering cross sections. First, the d sigma by d omega is proportional to square root of the atomic mass of the target atom, that is Z1 square, and accordingly the yield would be proportional to the atomic mass number. Second, d sigma by d omega is proportional to square of the atomic mass of the projectile atom Z2 square. Hence, heavier projectile would yield more compared to the lighter ones. Third, d sigma by d omega is inversely proportional to the square of the energy of the projectile, and the yield of backscattered particle would be proportional accordingly. Fourth, d sigma by d omega depends only on theta and hence axially symmetric. 5. d sigma by d omega is inversely proportional to the fourth power of the sin theta by 2 when m1 is very much less than m2. Hence, the reduced scattering angle yields more backscattered particles. Energy loss and stopping cross section. The large angle Rutherford scattering collision occurs rarely, and hence the energetic incident particle will enter into it due to the low angle scattering behavior. Backscattering spectrometry is an analytical method to the secondary process. Note that the first order process is the implantation of the beam particle into the target. Penetration of energetic particle into the matter can be estimated from the energy profile of the incident beam. As the particle impinges through the target, it slows down and its kinetic energy E is equal to half mv square decreases. The amount of energy delta E lost per distance delta x traversed depends on the velocity of the projectile, on the density and composition of the target. This can be realized by performing a simple experiment by taking a very thin target of thickness delta x and of known composition. A beam of particles impinge on this target edge in the figure below. The energy difference delta E of the particles before and after transmission through the target is recorded. The energy loss per unit length, also called the specific energy loss and frequently abbreviated as dE by dx, at energy E of the incident B is then given by limit delta x tends to 0, delta E divided by delta x equivalent to dE by dx whole energy E. For backscattering spectrometry, it is the energy loss of helium-4 in the elements at energies between 0.5 and 3 mega electron volt that is of chief concern, because beams of helium-4 in that energy range are most frequently used. Typical dE by dx values for helium-4 of that energy range lie between 10 to 100 electron volt per Armstrong. The next is stopping cross section. The energy loss dE by dx accounts for the energy that the incident particle loses when it comes in contact with the target atom during scattering. The value of dE divided by dx can be viewed as an average over all possible energy dissipative process activated by the projectile on its way past a target atom. Thus, dE by dx can be calculated as the resultant of independent contributions of every atom exposed to the beam. This number is Sn delta x if delta x is the thickness of the target, S is the target area illuminated by the beam, and N the number density in the target. The projection of all these atoms on the area S produces a surface density of atoms delta x. This quantity increases linearly with delta x, as does the energy loss delta E is equal to dE by dx multiplied by delta x. We therefore set delta E proportional to n delta x and define the proportionality factor as the stopping cross section epsilon, that epsilon is equal to 1 divided by n multiplied by dE by dx. The conventional unit for epsilon, or you can say small e, is electron volts square centimeter per atom. In a scattering process, the incident particle that interacts with the target during the scattering loses energy via many individual encounters, which is subjected to statistical fluctuation. For these identical particles having the same initial velocity do not have exactly the same energy after passing through a thickness delta x of a homogeneous medium. The energy loss delta E is subjected to fluctuations. The phenomenon is sketched in figure 4 called energy straggling. Energy straggling places a finite limit for the precision with which energy loses, and hence depths can be estimated by backscattering spectrometry. The ability to identify masses is also impaired, except for atoms located at the surface of the target. The reason is that the beam energy E before a collision with a specific mass M2 at some depth within the target is no more monoenergetic, even if it was so initially, so that the ratio E1 divided by E0 and hence the identification of M2 become uncertain as well. For these reasons, it is important to have quantitative information on the magnitude of energy struggling for any given combination of energy, target material, target thickness and projectile. Concept of Rutherford backscattering. The aim of this topic is to give basic idea about the concept of Rutherford backscattering with the help of basic concepts developed early in this chapter. It will give a sound knowledge on how scattering works and the related parameters are estimated. The schematic diagram of a backscattering system is shown in figure 5. A beam of collimated and monoenergetic particles of energy E0 is generated by a source as shown in the figure. Typically, a current of 10 to 100 nanoamps of 2 mega electron volt helium ions in a 1 mm square area is generated. The beam of monoenergetic particle falls on the target. After it hit the target, particles much less than 1 in 10 to the power 4 are scattered back out of the sample. A sample fraction of this incident is captured by the aperture of an analyzing system. In this way, we get analog signal as the output of the system. This signal is taken and fed back to a multi-channel analyzer, which subdivides its magnitude into a series of equal increments. Each subdivision is referred to as a channel and is given a unique number which increases by a fixed increment. Modern multi-channel analyzers contain thousands of channels. A count is defined as an event whose magnitude falls within a particular channel. Each channel registers a certain number of counts. The output of the multi-channel analyzer is thus a series of counts contained in various channels. A segment of such series from channels 132 to 134 is shown in figure 6. The corresponding counts contained in channel I is represented as Hi. The qualitative analysis of the spectrum can be done by the graphical display. Digital outputs are used for numerical analysis. Such a series of counts versus channel number constitutes a backscattering spectrum. In the graphical display, the ordinate is frequency labeled yield or backscattering yield. The analog signal recorded by the analyzer can be analyzed, which contains quantitative information on different parameters of the detected particle, including energy, momentum, etc. The backscattering spectrum obtained with such an analyzer is a backscattering momentum spectrum. A semiconductor particle detector produces an analog signal proportional to the energy of the backscattered particle. Correspondingly, a spectrum obtained with such a detector is a backscattering energy spectrum. The main component of the analyzing system consisting of energy dispersive analyzer, amplifiers and a multi-channel analyzer, and is schematically shown in the figure 7. Multi-channel analyzer can be replaced by a single channel whose position is changed sequentially so as to scan the range of the parameter measured. In general, there is a correspondence between the channel number and the magnitude of the particle parameter to be measured by the analyzer. The most desirable property of this relationship is that it should be exactly linear and stable in time. Other important points regarding the designing of the detector is a separate issue which can be optimized to get fast acquisition of data. The semiconductor surface barrier detector and a charge sensitive amplifier are used almost universally in backscattering spectrometry. So students, let us summarize what we have learned in this module. The four basic physical concepts which govern the backscattering spectrometry, including the kinetic factor, scattering cross-section, stopping cross-section and energy cycling, were discussed in details, and the concept of Rutherford backscattering was introduced. When the target is single crystalline, the cross-sections are clustered along sets of lines in space. If the incident particles moves in a direction parallel to such lines, and if the flux of these particles is concentrated in the voids called channels surrounding these lines, the probability of a scattering collision is reduced. This is the situation commonly referred to as channeling, which will be discussed in the later session. Laboratories engaged in backscattering analysis have developed computer programs to calculate backscattering spectra. Most of these programs are tailored to meet the specific needs of the respective laboratories. Mostly, Fortran program is suitable for this purpose. To calculate the differential cross-section for an elastic collision, the principles of conservation of energy and momentum are complemented by a specific model for the force that acts during the collision between the projectile and the target masses. In most cases, this force is very well described by the Coulomb repulsion of the two nuclei, as long as the distance of closest approach is large compared with the nuclear dimensions, but smaller compared with the Bohr radius A is equal to 0.53 angstrom. Thank you.